Hello everyone and welcome back. Today we're going to learn how to do analytical limits. So in the last video we learned how to do graphical limits and numerical limits. But those sometimes could take longer. So analytical limits are a much faster way. But before we get into them, we should know some laws. There are 11 laws. They're pretty self-explanatory. Just look over them and then you'll kind of just know them. But let's do an example with these laws. So we have these two functions f and g, and we're trying to find the limit as x approaches -2 of f of x plus 5g of x. What we should do before we do anything is we could split up the limit with the sum law and our constant law here. So we can make it into the limit as x approaches -2 of f of x plus 5 times the limit x approaching the -2 of g of x. Now we just look at our graph. As f of x approaches -2, we get 1. As g of x approaches -2, we get -1. Times 5, you get -5. And then 1 minus 5 is -4. Our next limit problem is going to be the limit as x approaches 1 of f of x times g of x. So again, we could break this up into the limit as x approaching 1 of f of x times the limit approaching 1 of g of x, which is law number 4, our product law. Now again, we just look at the graph. As it approaches 1, you get 2. But for g of x, as we approach 1, it does not exist because the left limit and right limit does not exist. So that means this whole limit does not exist. One last thing we could do, or one last problem, the limit as x approaches 2 of f of x divided by g of x. Now using limit 5, which is our division law, we have the limit as x approaches 2 of f of x over the limit as x approaches 2 of g of x. Now, for f of x, we get about you get like 1.4, about 1.4, but g of x we get 0. And in this law, g of x cannot be 0, so then the limit does not exist. Now let's do some more examples without the graph. So let's say we have the limit as x approaches 5 of 2x squared minus 3x plus 4. So to do these, to understand our limit laws, let's use them in this problem. So we could break this up as the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. So we could also make this as 2 times the limit as x approaches 5 of x squared, and this one 3 times the limit as x approaches 5 of x. And then using this law, number 6, for the x squared, if we just plug in 5, you get 25 times 2, that's 50. And then using law number 9, you get 5 times 3 is 15. And using law number 8, you just get 4. which means you get 39. Let's do a couple more. Let's do the limit as x approaches -3 of x cubed plus 2x squared minus 1 over 5 minus 3x. Again, using limit laws, we could make this up. We could break this up using our division law. So the limit as x approaches -3, -2 of x cubed plus 2x squared minus 1 over the limit as x approaches -2 of 5 minus 3x. There's a lot of breaking up to do here, so yeah, you could do the limit as x approaches -2 of x cubed plus the limit as x approaches -2 of 2x squared. But remember, we could take out the constant, so it's just 2 times that limit. And then the limit as x approaches -2 of 1, all divided by the limit as x approaches -2 of 5 minus 3, because we take out the constant, times the limit of x approaching -2 of x. So then this first one, -2 cubed, -8. This one is going to be 4 times 2, so plus 8. This one is going to be -1. This is just going to be 5, and then this one's just going to be plus 6, and then you get -1 over 11. So for each limit, you don't really want to show every single limit law. There's a lot. So there's something we could do called direct substitution, which is basically if you have a function that is continuous at a, which means you could draw the function without lifting your pencil. What the heck? Sure, that's our function. Since you can draw this whole function without lifting your pencil, that means you could just plug in a into your f of x, and that'll be your limit. So if you have the limit as x approaches a of f of x, let's just say that value is L. That's the same as f of a, which is L. So let's do some examples. Oh, I should probably keep that. Examples. Let's say we're trying to find the limit as x approaches 1 of x squared minus 1 over x minus 1. If you notice that if you plug in 1, you just get 0 over 0, and we don't know how to do those limits yet. So what we could do is we could factor out the top, which gives us x minus 1 times x plus 1. This is from this formula. I don't remember what it's called. Or B. It's from that formula there. And then this would be over x minus 1. We could just cancel out these, and you get the limit as x approaches 1 of x plus 1 is 2. So what else could we do? Let's do another example. Let's do a piecewise example. So let's say g of x equals piecewise function x plus 1 and then pi when x isn't 1 and then when x is 1. And let's say we're trying to find the limit as x approaches 1 of g of x. So for these limits, what we just do is we just find the limit from the right of 1 and the limit from the left of 1. So this would be our right. Actually, no. Wait. We just plug it into both equations, and we just see if it's the same. So if we plug into this equation, we get 2. When we plug it into this equation, we get pi. So the limit at 1 does not exist. Let's do another example. Let's just move this. Another example would be the limit as h approaches 0 of 3 plus h squared minus 9 divided by h. So when we plug in 0, again you get 0 over 0, which means we have to do some kind of algebraic manipulation here. So let's just expand this for now. You get 3 squared plus 3 plus 6h plus h squared minus 9 over h. These two cancels out, and we just have to divide everything by h. So we get 6h plus h squared divided by h, which equals 6 plus h. And we just plug in 0, we get 6. Now if you remember back in the last video, this one, as we used the numerical value, we got 0, but the value was actually 1/6. For that, we have to use a conjugate. So the problem was the limit as x approaches 0 of square root or x squared plus 9 minus 3 over x squared. So multiplying by the conjugate just means you do this part. Let's just make this shorter. And you times it by the opposite sign. So it would be square root x plus 9 plus 3 and then you want the expression to be the same. So this is also called multiplying by 1, because this whole thing is just 1. And then we keep this the same. And then you multiply everything out. So then you get x squared plus 9 minus 9 over x squared times square root x squared plus 9 minus 3. And don't forget your limits. From here, we could see that this cancels out. So then you get the limit as x approaches 0 of x squared over x squared times x squared plus 9 minus 3. Our x squares cancel out, so then you get the limit as x approaches 0 of 1 over x squared plus 9 minus 3 plus 3. Wait. Plus 3, yeah. So when we plug in 0, you get 1 over square root 9 plus 3, which equals 1 over 6, which again shows that this limit is 1/6. So now we're going to go over some one-sided limits. So if you remember what a limit is, a limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the right equals L, and if the limit as x approaches a from the left equals L. So let's do let's just go into it. Let's do an example. So if we have our function as f of x to be absolute value of x, what if we're trying to find the limit as x approaches 0 of absolute value of x? So absolute value of x might not have been defined to you yet, so we'll define it here. Absolute value of x is equal to the piecewise function. What the heck? The piecewise function when x is greater than 0, it's x, and when x is less than 0, it's negative x. So since this would be to the right and this would be to the left, we need the limit of x to be equal, limit of x to be equal to the limit of negative x. Oh, no more fishy, x. And that would be equal to 0. So since the right and left both equal 0, this would be 0. Now let's do another absolute value problem. So what if we have like the limit as x approaches 0 of absolute value of x over x? So let's write it as a piecewise function again. So this would equal, this would equal x over x, which is just 1, when x is greater than 0, and negative x over x, which is negative 1, when x is less than 0. So this is our right and this is our left. We need the limit as x approaches 0 of both of these functions to be the same. So limit as x approaches 0 of 1 should equal the limit as x approaches 0 of negative 1. And we can see that these aren't the same. So this limit does not exist. Now I'm going to pull out my old chapter 1 BC test, and we're going to do one of the problems I got wrong on there, which includes the absolute value. So this problem was the limit as x approaches negative 4 from the left of x plus 4, absolute value of that, divided by x minus x squared. So again, let's write our piecewise function. This would be equal to x plus 4 divided by 16 minus x squared when x is greater than negative 4. And this would be negative x minus 4 divided by 16 minus x squared when x is less than negative 4. So we just take the limit of both of those as x approaches 4. So the limit as x approaches, negative 4 of x plus 4 divided by 16 minus x squared. And then the limit as x approaches negative 4 from the left of, we'll rewrite this as x plus 4, but then with a negative sign outside. So for this, we would have to factor out the bottom. So in this one, you get the limit as x approaches negative 4 from the left of 1 over 4 minus x. Because this would be 4 minus x and 4 plus x, and this and that cancels out. On this side, it would be the limit as x approaches negative 4 from the left of negative 1 over x minus x, or 4 minus x. Now we just plug in negative 4, and then we get 1 over 8, negative 1 over 8 do not equal each other, so the limit does not exist. Next, we're going to go over something that you might see on your BC test if you're taking it. So let's say you have a function f of x that equals the piecewise function 2x plus 1, or 2x plus 1 and then k. And it's k when x is greater than or equal to 3, and when x is less than 3, it's 2x plus 1. So the question is asking for what value of k makes this function continuous. So for right now, we're going to understand with a graph. So let's graph 2x plus 1. It's going to be like this. I'll just make it dotted so you could see better. And k, we know k is going to be a horizontal function. Now what makes it continuous? It has to be the same as when it equals 3, when 2x plus 1 equals 3, or when you plug in 3 into 2x plus 1, which from this graph you can see is 7. But using limit language, what we could do, we can set the limit as x approaches 3 of this and that, and just make it equal, because you're saying that the limit from both sides at 3 is going to be the same value, which means it's also going to be continuous. So if we take the limit as x approaches 3 of k, and when the limit as x approaches 3 of 2x plus 1, you get 7. This is just k. And then you set the limits to be equal to each other, so you get k equals 7, which is true here, because when k is 7, the function is continuous. So now let's go over a harder variation of this problem. So we have f of x equals the piecewise function kx plus 1 when x is greater than or equal to 1, and x squared plus 3 when x is less than 1. So we just take the limit of both equations when x is approaching 1, and then we set it equal to each other. So this would be k plus 1, and this would be 4. K plus 1 equals 4, k equals 3. So when k is 3, this function would be continuous. Now we're going to learn about the squeeze theorem, which is one of my favorite things ever. It's also probably the first time you're going to have to write like sentences in math, which is also the only time I like writing in math, or in anything. Okay, so there's a couple conditions needed for this theorem. First, your function you're trying to find the limit of, which would be g of x, has to be enclosed between two other functions. So let's look at this example here. Okay, we put it here. So our g of x would be x squared sine of 1 over x. And we're trying to find the limit as x approaches 0. So from direct substitution, you get 0 over sine of 1 over x, or 1 over 0, and we don't know what sine of 1 over 0 is, so we would have to use the squeeze theorem. So what we could do is we could say sine of x is always between -1 and 1. And then you could just multiply everything by x squared, and then you get, oh wait, sorry. Because sine of x is always in between 1 over x would also always be between -1 and 1. Then after multiplying everything by x squared to get our original function, which is that, we get -x squared is less than or equal to x squared sine of 1 over x, which is less than x squared. So we have our conditions. We have this inequality, and then if we were to take the limit as x approaches 0 of negative x squared, that equals to the limit as x approaches 0 of x squared. Yeah, equals 0. And because this is also true, our original limit will also be true. But along with this theorem, you have to write like actual words. So I'll just do it. So our question is going to be, show that the limit as x approaches 0 of x squared sine of 1 over x equals 0. So to use the squeeze theorem, we need our two conditions to be true. This one and this one. So first you would say, since sine of x is less than 1 for all x in the real plane, it follows that the absolute value of sine of 1 over x would also be less than 1, which is also equal to negative 1 sine of 1 over x, and then 1. So now what we want to do, we want to get this inside function to look like the function that's in our limit. So we have to multiply everything by x squared. Multiply each term by x squared, which would give us negative x squared sine of 1 over x, and then x squared. And then you would say that the limit, which is our second condition, the limit of our outside functions are the same. Now, since we have our inequality and our limit, all our conditions are needed for the squeeze theorem to work. So we would say, by the squeeze theorem, since x squared sine of 1 over x is between negative x squared and x squared for all x, and the limit of both of those outside functions are going to be the same. Then you would say it follows that the limit of x going to 0 of x squared sine of 1 over x equals 0. So let's just go over what we did. So the conditions we needed to be true is our inequality and limit. And the first thing we did was show that that inequality holds. So usually on squeeze theorem problems, you would get either sine or cosine, and then their squared variations. And then you just make their range inequality. So you should know that for both sine of x or cosine of x, their range is negative 1 to 1. And then if it was squared, it would be 0 to 1. So you would say the absolute value of that is less than 1, and then this upside down a, what that means is for all, and then this whatever variable you put in this position is what you say here. So for all x, and then this little, I don't know how to describe that, this symbol means it's an element of whatever set you're in. So my set I used in this was the real plane, so that means no imaginary numbers. So x could either be like -1, 5, 2, but no i's. And then you want to get our inside of the trig function to look like the inside of our limit. And since it's for all x, what you change inside does not change the range. Then you just want to get it to look like the inequality, and then you multiply everything by, what the heck? Where did this come from? Then you just multiply everything by x squared, because that's what's in our limit function. And then you get the limit of our outsides, and then you have all your conditions. That's then where you say by the squeeze theorem, and then you just state your conditions, and then you say the rest. So let's do one more example. So show that the limit as x squared over x goes to 0 of 2 minus cosine x, let's do squared, over x squared equals 0. Yeah. So our trig function is now cosine x, so you would say since cosine squared x, this time you can't do the absolute value because it's not -1 to 1, it's 0 to 1. So you would say since cosine x is between 0 and 1, and you want that negative sign, so you just put this imply symbol. That's what that means. You just put that, and then you say you multiply everything by a negative, so you get 0 negative cosine squared x, and then less than 1 or greater than 1. The reason we changed our signs is because we multiplied by a negative number. And then now we want the 2, so you would just say add 2 to all terms. And then you get 2 greater than 2 minus cosine squared x greater than 3. What? Did I do that right? So for our next example, let's do show that the limit as x approaches 0 of x squared times 2 minus cosine squared x equals 0. So this time our trig function is cosine squared x. Oh, let's make it plus. So first you would say since 0 is less than cosine squared x, is less than 1, because those are the ranges of it. You could say, oh, I forgot my x. You would say for all x in the real plane, then you want this inside part to look like this. So you would say add 2 to each term, and then you get 2 less than 2 plus cosine squared x plus 3, or less than 3. And then the only thing we're missing is our x squared. So now we say multiply everything by x squared, and we get 2x squared less than x squared times 2 plus cosine squared x less than 3x squared. Now we take our limit of our outside functions, and then we get the limit as x approaches 0 of 2x squared equals the limit as x approaches 0 of 3x squared equals 0. Now since we have our inequality, which is this, and our limit, we can use the squeeze theorem. So by the squeeze theorem, since x times 2 plus cosine squared x is between 2x squared and 3x squared for all x, and their limits are equal, we could say that it follows that the limit as x approaches 0 of x squared times 2 plus cosine squared x equals 0. And that's all. So again, we stated our original trig function for all x, and then we just got closer and closer to our inequality, and then we showed our limit was true, and then we used the squeeze theorem. It's pretty easy. That's it. So I'm gonna post a practice problem sheet in the description, and then I'll post the video with the answers for that. There's gonna be like 3 squeeze theorem problems on there, so you can practice with that.